Okay, I'm here in Chattanooga, Tennessee at the branch headquarters, and I'm with Platt Boyd, the CEO of Branch Technologies. They're revolutionizing the possibilities of free-form design, mostly with facades, soon some residential projects with structural elements. Thank you so much for having me today.
Absolutely. I'm glad for you to be here. I've seen some of your podcasts in other locations, so.
Yeah, cool. It's always fun to do them in person, better than a Zoom call. There's so much with Zoom fatigue these days.
Oh yeah, definitely.
So we did a tour of your facility. How many machines do you have out there?
So right now, we've got kind of the fleet of 3D printing machines and then other machines. We have 14 printing robots right now. We've got 2 million bots. We've got R&D bot and then another bot in the works for foaming automation.
So your system, from my understanding, you print a lattice out of plastic or any material you can extrude, usually heat-based, and then depending on the utility, maybe for art systems, you might leave the lattice or you could fill it with foam?
Correct, yeah. So what we do is it's free-form 3D printing, where we 3D print a structural lattice like this that creates this what we call cellular network. And so this is a structural portion of that, and so it's a 2-pound piece about the size of a concrete block can support 3,000 pounds in compression, and that's the carbon fiber reinforced ABS. And then we infill with a fire-rated 2-pound polyurethane foam, as you see right there, and so that creates a composite, and that composite effect more than doubles the strength. It's about an R7 per inch insulation, so very high insulation value, but it more than doubles the structure. And so once you fill that block, so instead of 3,000 pounds in compression, it now supports 6,000 to 10,000 pounds in compression. And that's depending on the density of those cells. So density can create strength, and so we can kind of optimize to create strength where needed. And then we finish with either glass fiber reinforced concrete, which is what you see there, or a lightweight stucco that's a very thin finish to make rain screens for commercial construction or mega panels in partnership with panelizers throughout the U.S.
The mega panels are like what's on the bank?
No, those are rain screen panels, and so those are up to 4 feet by 10 feet. And the mega panels are up to 12 feet by 45 feet.
Wow.
So they're really just limited by logistics. And then we're the insulation and articulation on the outside of light gauge metal framing walls. And so it's, in that case, the value proposition is how do you clad a building 5 times faster than with on-site methods. So it's prefabrication to like a really great point.
On top of that, it would be so challenging. I mean, usually when you do a facade, specifically branch, every piece is unique, right?
Correct, yeah. So almost, not all projects that we do, but almost all projects that we do, every panel is unique. And that's the power of 3D printing. Like, it doesn't matter. Like, you could do flat panels or articulated panels, and they're going to be about the same price. It just has to do with like that inherent customization that 3D printing brings to the table. That's a really powerful tool in construction.
Yeah, I watched your webinar. To paraphrase something you said, you're really unlocking the power of the people that are working with the software. You have some incredibly talented software 3D modeling people here from great companies, and I'm sure they're really excited about being able to finally print some of the stuff that they've been working on.
Yeah. A concept called parametric design has been around for 25, almost 30 years. That ability has been in architects' hands for a long time. But the issue is that you could use that to create something really cool, but it just gets sequestered into like a digital model because the tools to actually fabricate that thing don't really exist too much. So it's either something that you can create it digitally, but you can't get it made because there doesn't exist any technology to make it, or it's something that is just, you can make it, but it's ridiculously expensive.
Mhm.
So one of the purposes behind Branch is to democratize design freedom and to make what has been available in the market to design and allow that into a broader set of projects into normal architects. And because I came from a very, very normal practice of architecture, and I couldn't touch some of these like very, very expensive budgets that some projects have. And so to allow that type design freedom into more normal construction budgets is really one of the purposes behind Branch.
Yeah, that's awesome. And so when you started the company, where did you get the concept from?
It started with a sketch, working too long on a Saturday on a very not fun project.
Were you still working in construction or architecture at the time?
Architecture, yeah. And read an article about 3D printing, and as it was applied into construction, and seeing some other methods out there that were using layered concrete to 3D print with, and it was like, okay, well, that's really cool for certain use cases, but that's not how modern buildings are made. Modern buildings are almost always composites, and there's multiple layers coming together into an assembly. And so the idea was just a sketch of like, how do you use 3D printing as a scaffold for normal construction materials? And so that was the initial idea, and I was an architect I've got 4 kids, and so I had a partner in a firm, and so I was like, okay, I think this is a pretty cool idea, but taking it forward was like nights and weekends for 9 months before, like, okay, this is taking the leap and doing it full time.
Yeah, 9 months before you jumped in full time?
Yes, and that was a major leap that I don't know, it was very uncomfortable, but I'm very, very thankful for it, and then now to see where it's come is, I don't know, it's kind of mind-blowing.
Yeah, we serendipitously ran into Tony at lunch today, the third number 3 guy. Who was the number 2 guy?
Chris Weller. He was my next door neighbor in Montgomery, and he was in architecture school at UVA, a brilliant architect, and so he had interned at my previous firm, and I said, would you want to intern at this little startup company? And he said, yeah. So at the end of the summer, I asked him, well, I don't know if you could take a break from architecture school to come on board. Being a part of a startup can be a good thing. And so he came on board, and so he got married a couple years ago, and they moved to DC, so he's no longer here, but he was integral to the beginning stages of the company, and just a brilliant autodidact that could learn almost anything.
Wow, I'm going to move the laptop so the fan is not right next to the mic.
Okay.
So, at what point did he join you? Before you left the architecture firm?
I left in April. I think he came on board in July, and then we did a couple things that summer, and then at the end of the summer he was about to go back to school, and I said, here's, would you be willing to take a gap year? And then the gap year turned into like 4, I think.
Wow.
But he ended up graduating architecture school from UVA in, I think, a 4-year program in 3 years. I mean, he just had done incredibly well there,
yeah.
So.
Cool. And so basically a year you were on your own. Did you raise money? Did you get a printer in that time?
No. So yes to the raising money. So we had to that was one of the first things. It was like, okay, we knew on savings we could take it only a little ways. 401k could take us a couple more months.
And that's basically like just financing your life after you left the architecture firm, or were there expenses at the beginning of the startup?
Oh, there's lots of expenses at the beginning of a startup. But that's how the initial thought was, okay, we can take it for a little while, my wife and I. But immediately I was pitching investors, and we got a round of investment in those early days. There was a small round, but like angel round.
Under $1 million?
Oh yeah.
Under 100,000?
300,000. And then took it forward for a while, and then we came to Chattanooga for an event called Gig Tank in 2014.
From where?
From Montgomery, Alabama, which is where I practiced architecture, and where we had been for 17 years. So, like, that was home.
Yeah.
But then investigated Chattanooga, one of angel investors said, "Have you heard of Gig Tank?" I was like, "What's Gig Tank?" And he said, it's a 3D printing business incubator based in Chattanooga. So I came up here to that in July, and there was like 1,000 people in the room, and 10 to 12 different startups pitching 3D printing ideas. And I was like, wow, this is the community. This is what is needed.
How many times had you done your pitch at that point?
Oh, at that point, not very many. And we didn't participate that year. But it was the community of, like, there's founders, 3D printing companies, there was investors from all over, and then Oak Ridge National Labs was here. And so they're part of the Department of Energy, and they were doing large-scale 3D printing. So
plastic?
In polymers and metals. And so, anyways, that's what began the journey here to Chattanooga. We went through it the next year after deciding this is a good place to grow a business, and moved the business here, and then moved into that incubator that I believe that you went to, and that's where we were for 4 years before this facility.
Yeah, it's a cool space. I just walked through, but it looks like a lot of young startups just hustling.
Yeah. And then I pitched the CEO of KUKA at a conference.
Before they sold to China.
Yes. And said, here's what we're doing in 3D printing. Would you be willing to loan a robot?
Wow,
for a
big ask.
period? Yeah. And eventually they said yes, and you can have it for 3 months. So we got a little 3-foot arm, and had that in a room about this big, with too much heat in one little space. And anyways, that was the first 3D printer that was developed. And then as we moved up here, within the next year, we bought a larger robot.
So by the time you got the printer, were you a 3-man crew?
We were, yeah. And then we're adding more people over time.
Yeah,
and
now you're at 50?
About, yeah.
That's incredible.
So, and 50,000 square feet here. And so it's a great group of people.
Yeah.
Like an amazing group.
So for those 4 years, at the end of the 4 years, did you still only have the one printer?
So by the time we moved out of the incubator, we had 4 printers in 5,000 square feet with about 30 people.
Wow.
So we were just crawling all over each other, and we moved in here, and our office is 5,000 square feet. And we've got a lot more room for spreading out and having product.
How was the initial vision different from what we saw here today?
So the initial vision was doing houses. And doing residential construction, custom residential construction. And after we did a project called Curve Appeal, we came to a point where we basically ran out of money. One, and then two, realized like doing this, I thought we would have to demonstrate something at that scale before people would trust it.
Yeah.
And we had done enough projects that were with matrix, that were pavilion scale type things, and had done enough analysis structurally to understand the capabilities. And we printed that whole project. And we got to a point where it was just, we had to start making money, like immediately. And we also realized that doing that house, beautiful as it was incredibly complex structurally. And structural engineering was going to have to kind of basically catch up with where the capability of the printing process was. And so it wasn't a scalable proposition because it took an incredibly sophisticated firm 9 to 12 months to engineer a house. And that's way too long. That's not scalable. So we pivoted to facades and for commercial construction. And in that arena, a facade is something, it can be lightweight. It's structural from a lateral load standpoint, but it's technically non-load bearing on the building. And so it's something that you can basically create beam tables. And here's our spans that we can do for certain panel sizes, and then the parametric design, the 3D printing is applicable to the articulation available on a commercial building, which architects have really been dying for design freedom for a long time, and so this enables that type design freedom. Yeah, so that project was wholly aluminum composite metal panels, and so we came in, the construction contract was already awarded on that, and we worked with the design builder and substituted our product for those flat aluminum composite metal panels.
That would have been a pretty boring building.
It would, yeah, and now it looks much better.
Yeah, totally one of a kind.
They said that they have gotten lots and lots of people that come to them as clients because of the unique building. So that's a pretty good value proposition for owners.
Yeah, for sure. So the structural system holding up the panels, was it the same as the aluminum, or were there any adjustments?
We did have to, I think, reinforce a couple little areas, but other than that, like it was metal studs. That was the skin of that building, and so our system attached to those metal studs.
Cool. So there's another really interesting project you did with a LiDAR scan of the moon.
Yeah, now that one's different. So that's for the U.S. Space and Rocket Center in Huntsville, kind of a really cool museum associated with NASA. And they were doing their new space camp building. We approached them. I can't remember how we got in touch with them. It was the same architect that we worked with on the Huntsville parking deck. And so they had this project, and they said, could we use your stuff on that? And so we developed a couple of different spacey kind of themes, some that were based on like propulsion going into orbit, others re-entry, and then kind of a themed, interpreted moon surface that looked like kind of Swiss cheese. Well, they liked that one, but they wanted more realism. So they said, we have this LiDAR scan of the moon that had 6 billion points to it. So way more data than was necessary. And so we took that and used that for the surface articulation.
Did you tone down the number of points?
Yes. And we took the articulation and made basically the topography of the moon have about 8 inches of depth. And so we're able to take that surface model and adapt it to our facade.
That's really cool that you can, I mean, it's just like regular 3D printing, but the models you make, they're like all infill. There's no shell.
Yeah, it's a solid model. What we end up using is a watertight geometry, and oftentimes the geometries that we get are not that, and so we have to fix it. And so that kind of gets into some of the digital process, and where we get a file, and it really doesn't matter. We're kind of agnostic to CAD programs, Revit, Rhino, CATIA, SketchUp, whatever, it doesn't matter. We bring it in, and then it goes through our digital process. And so we take that 3D model and then do a series of offsets for the different surface, the thicknesses and processes, because that model is the source of truth for us. It informs 3D printing, it informs the milling, the foaming and the milling, and then ultimately the final surface finish, and then how everything attaches back to the building.
Yeah.
So that model is something that on our internal processes, we've started transitioning to CATIA, which is more made for manufacturing, and so it can parametrically adapt to different geometries. You can change geometries, you can change details, and it will update all of the panels on a project almost instantly. And so that's something we're wanting to be a manufacturer, and you have to create automated processes and workflows in order to do that. But with a custom product, it's a consistent process through a custom product through a consistent process. And so on the digital side, that's one of the things that we've implemented to help that front-end workflow into the digital process of manufacturing.
Yeah, that's pretty unique for manufacturing. Usually they're producing the same thing over and over. And we've seen a lot of 3D printed concrete on this channel, but it has no tensile strength or flexural strength, and so when you put it on a truck to ship, if they're in prefab, it cracks, and so this seems much more shippable. It's lightweight generally. The file you start with, is it typically an STL or a step file?
Oh no, we don't want an interpreted geometry. We want the real model, the vector geometry, that is the real CAD file. That's what we start with.
And what do you export that to before you feed it through, I assume, your proprietary slicer?
So we can either take it from Rhino, like internally we use Rhino. If it's a small project, we won't go through CATIA. If it goes through CATIA, it outputs, and then it directly outputs to the software that takes the volumetric shape and then parses it to create that internal structure, either with what we call voxelized grid, where it's all the same, and it's like, if you remember the game Cubert, where, or think Minecraft.
Okay.
Minecraft on the inside of a panel. So everything is just cubes, and you subtract the ones that are intersect the face geometry. Or you can do a structured grid, and structured grids they conform to the surface geometry, and so for almost all the projects that we do with Matrix, they're structured grids, and so that is a process that you create that internal geometry, and then our software sequences the whole thing, creates the robotic code to tell the robots, here's how to print this thing. So that's all kind of on the software side.
Was there ever a point that you decided to get rid of having an external printed shell, or that was never even in the equation?
You're talking about the internal?
Externally, so usually a print is solid, like a small plastic print with like a Prusa or Creality, but you never had any kind of shell on the exterior even in the beginning?
No, I mean, this was meant to be a structural thing.
And use as little material as possible? Yeah,
and so think of it as configurable light gauge framing, like wood studs, metal studs. This is basically a configurable version of that. So there is the idea initially where it was going to be, you could 3D print decoration on there. That's a whole lot harder than it is to we have developed a way to do layers, and we can use those to attach parts together, or to reinforce areas, or to attach fasteners into what we print. But that's a slower process. It's not. It's using a whole lot more material, and we're trying to be as material efficient as we possibly can.
You mentioned carbon fiber, another type of material that's used in windshields. What are the different kind of materials you're experimenting with, and some of the pros and cons of each?
Yeah, so the carbon fiber reinforced ABS is our fastest, cheapest, strongest material that we print with. We've got PETG that we've printed with, and a biopolymer that's derived from sugarcane. The PETG and the biopolymer are both rated for interior exposure from a fire standpoint. And then ASA is another polymer. What we're beginning to do, and we're kind of almost at the finish line of characterization, is a new polymer that's a Lexan. And it is about 250% stronger than the carbon fiber ABS. Those numbers that I mentioned are the carbon fiber ABS.
Yeah.
The Lexan is substantially stronger than that. So, and we're still going through the full characterization for all the numbers and results.
It sounds crazy that the carbon fiber version is the most cost effective.
Yeah. I mean, we're using off-the-shelf polymers, so it's not something that you're using like a very expensive proprietary blend. ABS is what's in Legos, even though those are fairly expensive. The ABS is used in light covers,
Airsoft guns.
yeah, all kinds of things. My kayak is made out of ABS, so.
Very strong. I guess the carbon fiber, you just don't need so much of it, and it makes it much stronger.
It adds about 40% of the strength with the addition of the carbon fiber versus the neat.
Wow. So you're printing the lattice, but the automation doesn't end there. You have some other applications for the Kuka arms?
Sure, yeah. So we take the lattice, we fill it with that the fire-rated spray foam, and then mill that down robotically. And that's what gets you to the articulation of whatever surface a client is wanting. And that milling process is a secondary process. And so that is what translates the digital geometry into the surface finish.
Ultimately, how far from the last layer of plastic does the foam go? Is it right there, or is there an inch of leeway?
We put about 20 millimeters. I mean, you can see it right there. That's the back plane, and we similarly do that off the front plane. And so it's, and that's kind of what we've done. We can mill through anything pretty much, but we try to avoid the polymer. It's better not to mill through it.
And how was the permitting process, especially for the early projects? Did they have to do trial by testing?
Oh God, yeah, we've done trial by testing on everything. And so we've done structural, we've done fire, we've done moisture, expansion, contraction. We're doing now composite testing of everything. And one of the things that is kind of a new development that we're working on, which would enable us to go back to the housing stock and do that more scalably, is we've been working with SOM, Skidmore, Owens and Merrill, on a parametric structural finite element analysis solver, and then the characterization of our multi-material composite. That's a very difficult thing to do, because you've got, if you take, hand me that, the piece right there, composite. When you have like you've got the matrix in here, you've got the spray foam, and then you have the GFRC. You've got interfacial bonding between each of those layers. Well, you can characterize a singular material. That's fairly simple. But when you start getting into multi-material composites, it becomes a very, very complex problem, like DARPA hard problem. And it's something that you have to do immense amounts of testing to characterize it, and then you can infer, here's the structural performance of that composite based on all that testing. And so we've been testing for years now to understand like all of the different characteristics of that. And that then flows into like a finite element analysis structural engineering solver.
In software.
In software. And so every building, this commercial building, goes through some sort of a structural engineering process. Typically, post and beam method construction, steel columns, steel beams, concrete, whatever. Those are very, very known values. Like that book, the green book back there, is the Steel Bible. It has known steel properties from 100 years. And so what they went through to test all of those section properties over 100 years, we're beginning to do for a multi-material composite. And so that's loading into, sorry I'm geeking out about this, but this is loading into that software solution so that they can analyze a geometry and say, yes, it works, no, it doesn't. No, it doesn't. Here's the problem areas. You change the geometry a little bit here, and now it works.
Yeah.
And so they're able to do that analysis in seconds now, versus months of what it was on that first project. So that was a huge development necessary in order to get to where we can begin to do the inherent customization that 3D printing brings to the table, but do it with the structural engineering necessary to make it code compliant, safe, and vetted by normal structural engineers. So that's a big initiative that is about 90% complete now.
Nice, that'll be incredible. So in the time being, when you're doing something like the facade project for the bank with so many unique printed pieces, there's no way you had to break each and every one of them, right?
Oh, no. So previously, the engineers only engineered around this, a thin shell concrete structure, 3/4 of an inch. Well, that's super weak. So when we've tested things, it's 5 times stronger as a composite as it is with just that thin shell concrete. So we had to re-engineer a project, and I was like, oh my gosh, because the engineer only did it with the singular material, and that's a very expensive prospect, so it was a good lesson learned, but it kind of pushed us towards this multi-material composite characterization project. Therefore, we don't have to go through that again.
Yeah. So would it have been easier for you if they approached you before the architect designed that project?
It would have been impossible.
Wow.
Like, there's no way, because we hadn't done all the testing. There would be no way to characterize it.
So going into their project after they already had the plans was a benefit?
So they designed around our capabilities.
The bank?
Well, yes, that one, but then the one that I'm thinking about is was a parking deck, and it was one that was done with much larger panels.
The mega panels, or?
Well, yeah, kind of up to 20 feet, 8 feet by 20 feet.
Wow.
For that project. And so that one was engineered around a thin shell concrete, not taking into account the everything that we're bringing to the table in the composite.
Yeah.
So
they get more than they bargained for.
yes.
How did you transport those? Were they, that's too heavy to be moved by hand?
Oh, definitely. I mean, that was, big flatbed trucks, and you crane them onto the building.
With a couple pallets and forklifts, or?
No, those those
inside.
weighed anywhere from 2,000 to 5,000 pounds.
Wow.
Those were very, very large GFRC panels. Our typical rain screen panels are a couple hundred pounds, and can either be picked or with the lightweight stuccos, you can just pick them up by hand.
So how do you get them out of the facility?
Oh, we got forklifts,
Mm-hmm.
and you can lift a lot of things up with a forklift.
Were there any damage in transportation?
Sure, yeah, and you got to fix those.
I guess the concrete's the most brittle part.
Yep. And so we had to repair those that were damaged. And first of their type projects, you have to follow through all the way and make it good in the end. And that was a first of their type project. And so thankfully, we've engineered now around a lot of that. And so it's something that is definitely a more robust product now.
Yeah, the nature of your business is kind of begging for lots of never before done projects.
I mean, we've got a pin. A guy, one of the people made this pin, and it's first in the world.
Nice.
Because a lot of the projects that we do are first in the world.
Yeah, I guess that's the beauty of a dynamic 3D printing system where you can have so much customizability. At a certain point, you understand it so well that something brand new, never done before, is maybe perhaps well understood with the composite testing system.
Well, if you're doing first of their type stuff, you almost always have to test
Yeah.
and get it to, you've got to do a lot to get that to code compliance. So that, I mean, we've spent years and millions of dollars on testing and certification to commercial code compliance.
Is most of that with the local municipality?
No, that's to international building code. So it's the commercial construction code. Oftentimes in the U.S. is governed by the International Building Code, and that's what most municipalities have adopted. And so that's what we have tested to code compliance on those standards.
Are you part of Joint Group 80?
Joint group.
With Stefan Mansauer and those guys? I guess it's more of a concrete thing, but okay, so would those standards apply outside of Tennessee now?
Oh, definitely. Like, that's across the U.S. And then international places that say, oh yes, we'll accept the U.S. codes and testing that you've done. We'll see how applicable that is. Most countries have unique building codes.
So going forward, you've now got all this work done, especially in the structural testing software, all proprietary. Is your business model to produce these systems, or will you ever be selling printers?
So the business model is to produce product
Mm-hmm.
and sell custom products. And so that's what we do as a business. There's enabling technology, enabling software, hardware that allows that, but that's not what we're selling. We've had people that have asked, do you sell your printers? And the answer is no. What we sell is the enabled product from the process. So that's a big differentiator on kind of our business model compared to a lot of other people in 3D printing land.
Certainly, you're selling the product rather than a lot of people just sell the printers and they never operate them themselves, and so the customers end up with all these struggles.
Yeah, 3D printing is a great technology, but it is new, and it takes an expert to operate them effectively, and so that is something that you can either train somebody to become that expert, which takes months to years, or you can become the expert yourself, and that's what we've chosen to do.
So of the 50 people, how many can operate the printers?
About half.
Wow, that's a lot.
Yeah. I will say I used to could operate the printers, and a lot of people on the technical team used to operate printers, but I wouldn't want to touch it now. It's gotten more and more sophisticated,
Wow.
and the controls are just different, and so like I haven't operated the robots in, I don't know, probably 4 years.
That's a sign of a good company, I think, when you can hire people that are better than you at their job.
Absolutely. Yeah, that's one of my goals, is to always hire people that are better and smarter than who we are right now. So,
And humble too.
yeah.
The 14 printers you have out there, is it one-to-one, so one person operates one printer at a time?
In the early days, yes, and through automation now, we've gotten up to 8-to-1
8 to 1.
operator to robot
Wow.
ratio, and that's one of the goals, is that you are operating in a manufacturing environment, and so you want those to be almost autonomous.
Mm-hmm.
So that's the goal. That's the power of robotics, and when you can refine a process, it gets better and better over time, and that level of automation goes up.
Yeah, so that one person watching 8 printers, are they making sure there's no spaghetti? Is that the primary objective?
They're looking at quality control.
Mhm.
They're making sure that prints get submitted to the right robots. They're taking parts on and off platforms. So they're doing a number of different things. Quality control is probably the number one thing, though.
When you're doing concrete, there's a lot of human interaction, whether it's supports in the middle, but your system, if you complete one object, it's like a regular 3D printer where there should not be any human interaction during the print?
Sometimes there is,
Mhm.
for quality control issues, and so that's when and we've got kind of automated pauses in there where they're testing strength to make sure that it meets certain criteria for joint strengths.
How do they test that?
They've got a pull tester
Wow.
that is, you have to pull it until it reaches a certain level, and then you know, okay, it's going to perform to that standard.
If it doesn't, are they able to like plastic weld it together, or do they have to start over?
If it doesn't, they have to restart that layer.
Wow. Oh, they're just a layer.
Yeah, so they have to take it off and then restart that layer.
And is that just snapping the pieces off?
Sometimes it's harder than others.
Mhm.
So yeah, but it's pulling that layer apart. The sooner you do that, the better. And then the other thing that they have to do is, like, sometimes we'll put like an attachment mechanism into a print mid-print, so that you can fasten certain fasteners into something.
Mhm.
And so they'll insert some device into the print mid-print, and the robot will stop and tell them, put X into this location.
That's good. The robot tells you, so you don't need some paper with the steps and know each layer.
No, that would be very difficult with kind of how we're doing things.
Mm-hmm. At scale. So the testing happens how often? How many layers?
That's a great question. I don't know. The operations folks would know that.
Enough that one person can watch 8 of them.
Yeah. So, and it's amazing to see what new polymers are doing to that, and how it can become even stronger. Like that just blows my mind. How material science is such a big deal, and I think in construction, we've talked about building science. Building science is typically how do you put a building together and get it constructed. It's not the true science of like how all of these materials interact with one another and what are the innovations in the different materials that can be applied into construction. And so we're beginning to apply material science into like a new way of making, and we feel like we're just at the beginning points.
Yeah.
Because we're using as much as we can off-the-shelf materials and putting them together in a new way. But once you can start to optimize materials for performance characteristics, it's truly amazing what can be created with that. So like there's all kinds of areas of innovation there.
Mhm.
So.
What was the reaction from the other subcontractors on the bank job?
So most of the subcontractors didn't really have much to do with our stuff.
They weren't quivering in fear that their jobs would be automated away?
No. Uh, they, it was the rain screen installer that dealt with our stuff the most, and then the windows, like flashing around the windows. In like the typical workflow on commercial construction, we're interacting with the people that make the envelope.
Mm-hmm.
And so that's typically where we're interacting. Long term, when you're applying innovation and 3D printing into construction, it has effects that are larger than what we're focused on right now. Where you're beginning to bring labor efficiency, you're multiplying labor, you're creating solutions to the skills gap that's occurring and the lack of people coming into the construction market. So that's where everybody's afraid that robots are going to take my jobs away. Well, the jobs are, like, the people are leaving the jobs and nobody's coming in.
Yeah.
And so there's a huge labor gap that's beginning to be exacerbated in construction. And so this begins to help multiply that labor to begin to solve some of those issues. But I call this digital craft. It is not solely digital. There is a craft element because there's people involved at each step, and those people are vital. Robots are stupid, really. Like, they do what you tell them to do, only. Like, integrating intelligence into it is way down the line.
Yeah.
But a robot is good at certain things and really bad at other things. A human is amazing at certain things and really bad at repetitive, mundane tasks or unsafe tasks. And so that's where the robotics married up to a human is a wonderful combination. But we're trying to, like, make that fit together.
Yeah, it seems like young people want to have a standing desk with double monitors rather than swing a hammer, and so you're facilitating their ability to do that and it still be contributing to construction.
Like, one of the things that's interesting is, like, our workforce is typically, I'd say about 30 would be the average age here. And so that's not typical on a construction site. You've got a generation of people that'll be retiring out over the next 10, 15 years, and there's not a lot of young people.
Those guys call their grandkids to start their computer.
So we've got people that are fresh out of high school or a trade school or college coming in and doing different activities here, and it's wonderful to see a new generation of people coming into construction, but not construction.
Mm-hmm.
Like, it's not thought of as construction, but it's a, I don't know, a new workforce coming into this industry.
Yeah, there's so much knowledge in the folks that don't want to use the computers on the job sites too, in terms of being on site, and just construction in general isn't always the same as it seems on a computer. Have there been scenarios where somebody not very tech oriented has contributed to some kind of ideation or?
Oh gosh, yes. So I've had to learn a lot about, like, manufacturing.
Mm-hmm.
And because I came from architecture, which is not a manufacturing-centric profession. But one of the things that resonated the most with kind of our core values and how we operate is, and I've said it from the beginning, is this is an open ideas company. Anybody can come up with an idea, and the best ideas bubble to the top, and that's what we're going to use. And so we encourage everybody here to come up with ideas and to say, I think we could do this better by X, Y, Z. And I read this book and understood that it's a method. It's called the Toyota method, Toyota management system, Toyota Kata, and it resonated with me, not a manufacturing person, because what it does is it enables anybody in the company to come up with an idea to solve these problems. Well, the people that are actually doing work are going to have the best ideas because they deal with these problems all day, every day. Thinking that I can come up with an idea that's going to be like top down and solve somebody's problem, it may work every now and then, but it's way better if it's bottom up. And so we read that book as a company, I don't know, a year or two ago, and it was like an empowering thing for everybody here to understand I have a voice, what I'm doing, I can contribute to this, and my ideas will be heard, and the idea that I have may improve our performance by 5%, 10%, 30% on whatever process. All those things aggregated together make a much more efficient process.
I was going to ask how you facilitate that culture within the company. I guess having everyone read the book is a great start. From there, in practice, is it open door policies? Is it group meetings? How does it...
So we do a number of different things, but like one kind of big picture thing that we do is we have quarterly planning, and during that quarterly planning, everybody in the company is involved, and we have lessons learned, like what was good, what was bad, what was ugly, and anybody contributes to those lessons learned, and then we base our priorities and some of the things that we do within each quarter on those things. And then another thing is we have like a demo day every quarter. Like anybody can pitch an idea, say, I think we should be doing X, and they have to pitch it, and I can't remember what percentage, but it was over 50% of those ideas have been implemented.
Wow.
And it's amazing to see what people come up with. So I love that aspect of the culture here.
You mentioned your wife earlier. Does she get involved in the company at all?
No, she has been a huge support, and been something that I couldn't have done this without her.
Yeah.
But in the day-to-day operations, no. And so I bounce ideas off of her.
Yeah.
She's a very wise, kind person, and has the support needed when you're going through like crap when it hits the fan. But she is a designer more so than a fashion designer, more so than like manufacturing, that kind of thing. So, anyways.
Did your kids stop by and check out the prints?
Oh yeah, my daughter worked here one summer.
Oh, cool.
And she was doing fabrication, and then another daughter helped write grants, and my son comes here, like when I'm here on a Saturday, he'll be riding around with his little hoverboard thing.
Okay.
So.
Do you take any of your work home with you in terms of like the physical printed objects?
Take a lot of work home, yes.
Like
physical things,
nothing
not
printed
so
in your
much.
house?
No. I think that doesn't go with the aesthetic of our house. It's just, I don't know, different.
Yeah.
So.
Would you ever live in a building that you printed?
Oh, absolutely. I think that house that we did was the sexiest house I've ever seen in my life. And like later in life, when you don't have kids, it's, I think, one of the most beautiful structures I've ever seen.
Why would you wait till your kids move out? Is it smaller?
One bedroom house.
How many square feet?
It was about, well, footprint-wise, it was 3,000 square feet. So it was a really big footprint.
With major sloping arches.
Yeah, and lots of outdoor like space. I think enclosed it was about 1,200 square feet, but 1 bedroom, 1 bath, like living area, kitchen area. So voluminous spaces. So we fit our entire company in the bedroom. When we did a pre-assembly of it, and about 45 people in the bedroom. So that's not a typical bedroom.
Certainly luxury.
Yeah.
What does the company need the most right now to grow and scale?
So a couple different things. One is we're a startup and constantly raising money.
Mm-hmm.
So that's one of the things that we're doing right now. We got an open round and hopefully closing that in the next couple weeks.
Cool.
So that's one of the things that I've had to learn how to do is pitch and raise money. Two is we're looking for collaborations out there. And by that I mean like working on projects together, doing commercial construction, that's our focus. And so designers, architects, constructors, working with them to take those projects from like the idea phase into reality. And so always looking for projects where we would be applicable on. And then third, we have several open positions right now in kind of key categories for us. And so I know we're Director of R&D is one, COO is one, Senior Manufacturing Engineer, Head of Sales, and I think there's a couple others in different categories. So almost constantly hiring.
Is there an official title of the round you're on? Is it a seed round, A round, B round?
So the last round was B round.
C
This
round.
is kind of this won't be a C round. It's not a good time to raise a C round.
Okay. B and B.5.
Yeah. So.
Cool. I guess, yeah, that's a reasonable step towards, would you go public one day, or is that in?
I mean, there's several different ways that investors get monetized out of something like this. Public is ideal. The 1% of 1% of 1% of companies do that. There's other scenarios for monetization.
I think you already got to the 1% of the 1%, so it's only a couple more 1% to go.
So, but you have to have scale and lots of production, and we're not there yet. Like, kind of our long-term goal is to have multiple facilities across the U.S. and around the world that are producing products at scale. That's our long-term goal, and it's something that the construction industry is so incredibly massive that like we've only just begun to touch that potential.
So what does your ideal client look like?
So we want to work with building owner-operators that want a differentiated product in the market, where they want clients to, for them, it draws business in, it sets them apart in the market, it does something that's different than all the boring boxes that are out there. And so that's the owner-operator, and then second is like the architect. Because we enable the design freedom that oftentimes architects have been dying for. And enabling that within more normal construction budgets. So that, and doing that on buildings that wouldn't typically get a feature design on it because it's a normal construction budget. And so that's kind of the second category of who would be an ideal client.
Yeah, it's cool to see things that wouldn't be really possible without the technology you've developed, like making a bunch of elements that are totally unique. You need to make unique formworks for each of those previously, and then what do you do with them afterwards? You have to take it all apart. So I guess people with unique concepts, maybe they've been told no in the past.
Oh gosh, I can't tell you how many times I've got my hand slapped for coming out with, oh, this would be cool. No, you can't do that. And so this kind of enables that instead of it being no, you can say yes. to that unique thing. And that's fun. That's a lot more fun. And it's amazing to see when someone begins to realize what the possibilities are and the wheels start turning, like their mind goes crazy. Like, and they start thinking a million miles a minute.
Have you worked with any universities to start teaching their students how to work with your technology?
So I've given some talks at
Mm-hmm.
different universities over the years. We haven't done any kind of like partnership or class or anything like that. There's a lot of stuff, content online, that either talks that I've given or on our YouTube channel that has kind of design principles or the different methods that we go through, and it kind of illustrates those. And we also have some design guides that say here is all the different features that are possible within the possibilities. And so that's stuff that we give out. And
What's not possible?
not possible. That's a great question.
Right now, at least.
Right now, yeah, we're trying to stay focused on commercial facades.
Mm-hmm.
We get tons of inquiries for houses, and we basically say no to that. That's just completely different market. And there's other people out there that can do houses. But what's not possible? Everybody thinks you can do anything with 3D printing,
Mm-hmm.
and that's not true. Like, you cannot just do anything. One day, maybe you can like have the Star Trek replicator and it just pops out something.
Yeah.
But we're just not there yet.
Some of the SLA stuff gets pretty close to that. The light stereolithography.
Yeah. No, the thing, I don't know how much more time we have, but the thing that I think has the most potential with what we're doing is the concept behind this is like observing all that stuff. That was stuff that I had in my office way before the idea for Branch. I called it some of my beautiful and amazing collection. Just things in nature that you see that are just truly, truly phenomenal on how they're formed at the micro scale, like a radiolarian, macro scale, USGS satellite pictures that are probably maybe 40 miles wide. And so seeing those patterns and then distilling out like, okay, there's a structure underlying all of that, and it's cellular. And so the concept behind this is taking that type structure and translating that into how you can make building constructed things with a cellular mindset.
Mm-hmm.
And so we're working with a very, very simple cell that's just cubic right now. But if you understand 3D printing and material deposition in space, then you understand that you can do almost anything with that mindset. And we're at the stage 1, 2, 3 of where this can go. But with a cellular mindset, you can make almost anything. And that was the purpose behind the name Branch, is that we can branch into other things over time. And that, because you can make almost anything with a cell, that's why.
Yeah, biomimicry is so cool when you can find inspiration from nature. Seems like you've done a lot of that.
Well, I mean, still, one of my favorite times of the week is when I just take an hour and I will like surf on Pinterest and find all these just truly amazing things. Like whether those are pure math and fractals, or like you get into like the natural structures or just the beauty that you see in nature. That's truly inspirational for me. So
Cool. So if anybody wants to work here, they have a project, how do they contact you?
So we've got, through our website, we've got online forms, and that's how kind of the initial inquiry starts. And then we've got salespeople that are regional in different parts of the U.S., and that they'll start getting in touch. And then we've also got tools and literature on our website in order to say here's what is possible with these initial products.
And what kind of information should a potential client include in their initial inquiry to be an attractive thing for you guys to respond to?
So, like, mainly it's just, do you have a project, and is there a budget? Do you have an idea of what you want that project to look like? And whether that is something that the firm or the entity can 3D model the whole thing, that'd be great. If not, we collaborate, and we've got a design assist team that can create all kinds of content. And so we'll create something together. So that's what we oftentimes do.
Awesome. Well, thanks for letting me stop by
Yeah.
today, Platt. It's a
Thank
pleasure.
you, Jared.